Welcome to differential equations and Taylor polynomials. So recall in our earlier video on differential equations and power series, so in the video that was section 8.6, part 4, we found that populations could be modeled with a population growth. So we found that population growth could be modeled with a differential equation. And we pretty quickly, found a sort of general formula for our nth derivative of p evaluated at 0, right? And so we were able to come up with a formula for our entire power series. But what if instead of that simple p prime equals, what was it, 0.004 times p? What if instead the model were p prime equals 0.002 times, in parentheses, p squared minus 5,000 p, with initial condition p of 0 equals 4,000. So if we want to go about doing our power series, right? So if we wanted to do our power series, we would get that our a sub n's are equal to our nth derivative of p evaluated at 0 divided by n factorial, right? But that nth derivative of p evaluated at 0 might not be so easy to find. But that nth derivative of p evaluated at 0 is not as easy to find. So what we do is, instead of finding the entire power series, we just find a Maclaurin polynomial. So instead of finding the entire power series, we approximate with a Maclaurin polynomial in this case, because we're using just c equals 0. So in this problem, we were asked to find the third degree Maclaurin polynomial. So we know that p of 0 is 4,000. So that means that our a sub 0 is p of 0 over 0 factorial is just 4,000. Then we have p prime of t is equal to 0.002 times p squared minus 5,000 p. So p prime of 0 is 0.002 times p of 0 squared minus 5,000 times p of 0, or 0.002 times 4,000 squared minus 5,000 times 4,000. So that should be, let's see, if we plug this into our calculator, we have 0.002 times 4,000 squared minus 5,000 times 4,000. And I get negative 8,000. So what this means then is that our a sub 1, which is p prime of 0 over 1 factorial, is negative 8,000. Next up, we need the second derivative. So the second derivative of p should be equal to the derivative of that of p prime. So this should be the derivative with respect to t of 0.002 times p squared minus 5,000 p, which would be 0.002 times, we would have 2p minus 5,000. And then we would have to multiply by p prime for our chain rule. But that p prime, we know, right? So we have the second derivative evaluated at 0 is 0.002 times 2 times 4,000, that's p of 0, minus 5,000 times a negative 8,000. So if we multiply this out, we have 0.002 times 8,000 minus 5,000 would be 3,000 times a negative 8,000. And we get negative 48,000. So we have that our a sub 2 is that second derivative evaluated at 0 divided by 2 factorial would be a negative 48,000 over 2, otherwise known as a negative 24,000. Again, we need to go one more to find our degree theta Maclaurin. We need that third derivative of p. So that's just going to be the derivative of our second derivative. So that's the derivative with respect to t of, we had 0.002 times 2p minus 5,000 times p prime. So this would be 0.002 times, we can do a product rule here. So the derivative of 2p minus 5,000 would be 2 times p prime. And then we would have to multiply by p prime. Then to that we would add 2p minus 5,000 times the derivative of p prime, which would be that second derivative. And you absolutely could substitute in what p prime is. We have a formula for p prime. You could substitute that in as well. You don't have to do all the derivatives with the primes involved, or you can keep them. Either way is fine. So we have that the third derivative evaluated at 0 should be 0.002 times 2 times p prime squared. So p prime of 0 was a negative 8,000 squared. Then we will add to that 2 times p of 0 was 4,000 plus 5,000. And we multiply that by the second derivative at 0, which was a negative 48,000. So if we plug this into our calculator, we have 0.002 times 2 times 8,000 squared. Then we add to that in parentheses, 2 times 4,000 would be 8,000. Should that be a plus 5,000? No, that should be a minus 5,000. Sorry. So we have 2 times 4,000, we have minus 5,000, so that's 3,000. So plus 3,000. Times negative 48,000. And that gives me negative 32,000. So we have that our a sub 3 should be that third derivative evaluated at 0 divided by 3 factorial. So we are looking at a negative 32,000 divided by 6. And that's negative 16,000 over 3. So our third degree polynomial, our p sub 3 of x, our third degree Maclaurin polynomial, we had our a sub 0 of 4,000, a sub 1 of negative 8,000. So we have 4,000 minus 8,000x. Then we had our a sub 2 was a negative 24,000. So minus 24,000 x squared. And then we have minus 16,000 over 3 x cubed. So as you can see here, this will very quickly drop down to a negative value for x. That's because our population was decreasing so fast. At x equals 0, since we had a population of 4,000, we had a decreasing population to start off with. But this would be our third degree Maclaurin polynomial modeling this situation. So you can get a kind of an idea of what it looks like, at least close to x equals 0. We would probably want to go out much further in this particular case for our approximation to have an accurate model. But again, this is kind of the idea, one place where these polynomials come in handy. You can kind of solve a differential equation that you might not otherwise know how to solve. I know it was a little annoying to do so, but you might solve a differential equation you might not otherwise know how to solve using this technique. At the end of the class, we will see likely how to solve a differential equation of this form in a neater fashion than having to use Maclaurin polynomials. But this is one way that it can be done, and if we have a much more complicated formula, this can come in handy.